Hi, welcome back to differential calculus. In this video, we're going to go over a technique for differentiating certain functions, and that's called the power rule, or sometimes called the exponent rule. All right. So before we get into the mechanics behind power rule, what we need to understand is what it's used for. So sometimes professors do this thing where they just jump into how to do it, but you really have to understand what kind of functions it's for. And the short answer is what power rule is for when you want to differentiate or take the derivative of a polynomial. So what is a polynomial? Well, let me just use some generic functions. Okay, so let's say I have y, it's a function of x, and let's just say the function is something like, let's just say just simply x squared. All right, so how do you recognize a polynomial? Well, you're going to have some simple variable like x, and then it's always going to be raised to some numerical power. So that power could be 2, 3, 4, 5, it could even be 1 in some cases. All right, we'll actually see that. Another example is maybe you have y is equal to x to the 7th. All right, again, I just have one simple variable here, x. Okay, most of the things you're going to see are in terms of x. One simple variable, and it's raised to a numerical power. Another example could be even x to the 1000th. Okay, it's still just one little variable here, x, and it's raised to a numerical power. Okay, so that's something that's really important to recognize. I could also, in some cases, maybe I have, maybe instead of just having this function here, x to the 2nd, or x to the 7th, or x to the 1000th, I could throw in a constant. Maybe it's probably a number, so maybe I can throw in a 5 in front of it. So 5x to the, we'll say to the 9th. Okay, so what do I have here? I have this x to the 9th. It's just this little variable x raised to a numerical power. But notice it's multiplied by a number first. And from a polynomial's perspective, it doesn't matter if there's just the simple, x squared, or x to the 9th in this case, or it's multiplied by a number. Okay. Now, what would not be an example of a polynomial? So all of these are examples of polynomials. What would not be a simple polynomial is if you had something like this. Y is equal to x to the 5th times, and it's important to note this is multiplication, times something that we're going to talk about in another chapter, basically, times cosine of x. Okay? So in other words, what I have here is I have this x to the 5th, and you may say, okay, that's a simple variable raised to a numerical power, but then it's multiplied by this. And this is a trigonometric function. We're going to talk about those later. But whenever you have basically a polynomial multiplied by something that's not a polynomial, then automatically you cannot use power rule for this type of function. Okay. Another example that you could not use it for, suppose you had x to the 3rd, maybe we throw a constant out here, 4x to the 3rd, and this is something right here that could be differentiated using power rule, but suppose this was multiplied by, I'm just trying to think of an example, suppose it was multiplied times the natural log of x. Okay, natural log is another function we're going to see. Again, we do have this polynomial right here, but it's multiplied by something that is not a polynomial. Remember what a polynomial is it's whenever you have some variable like x raised to a numerical power. Natural log of x clearly is not that, and neither is cosine of x. So this could also not be differentiated by simple power rule. Okay, so it's important to recognize things that can. But there's another type of function that you actually could do. So let's suppose now I had y is equal to, let's say I had 3x squared, right? Hopefully you recognize by now that could be differentiated with it because there is a constant out here, 3, but it's multiplied times one variable to a numerical power, 3x squared. But what if I instead add on to it? Let's say I add on 4x to the 5th, right? Let's say this is my function y, okay? Well, then what I can do is I can say, well, these aren't multiplied together. They're separate terms. Okay, so can I take power rule with this? Yes, because it's some variable raised to some numerical power. And you can also do the same thing with this because it is a variable raised to some numerical power. Okay, and it doesn't matter that there's a number multiplied by both of them, you can still do power rule. Okay, you just cannot do power rule whenever you have some function that's multiplied by something that's not a polynomial. Okay, so hopefully that makes a little bit of sense. All right, so anything that I have here, so this group of functions up here, those are all something you're able to do with simple power rule. And then this right here, this is also something you're able to do with power rule. All right, so what I want to do now is really talk about how you do this computationally. All right, how do you take a function that's in the form y is equal to cx to the n and take the derivative of it? So what does this mean? Well, c is like the constant. Okay, that could be like the 5 here. The c could be the 5 that's right here. It could be the 3 right there, the 4 right there. It's just usually some number. And then this constant, notice, is multiplied by some variable x to a numerical power. So n is just a number. This could also be, this could be a 3, it could be a 7, it could be a 9, it could be any number. So notice what I have here. I have something like this, 3x to the 4th. So 3 would be the c, x would be the x, and this n, in this case, would be 4. Okay, so we're going to look at how do you take the derivative of something that's in this form. All right, here's kind of the way to think about it. All right, what I'm going to do when I take the derivative is I'm going to take this n, and I'm sort of going to think about just pulling that n right in front of the c, or if there's no c in front of the x, but basically just pull the n in front of the function. And then whatever's on this x, I'm just going to take that n and subtract 1. Okay, so the derivative, which we indicate either with y prime or dy dx, I tend to use this nomenclature, dy dx, but you're welcome to use y prime in Calculus 1. So when I do this, when I pull the n out in front, here's the n right here, whatever that number is. I keep the constant c out there, and then it's still times x, but x is raised now, instead of the n power, it's n minus 1. All right? So this may not make a lot of sense right now, but let's actually go into how to compute it. So here is a function we want to differentiate using power rule. Y equals 3x to the 4th. And based on what we had talked about, it's a polynomial. It's some variable x raised to a numerical power. And this is something we can do that. So let's take the derivative, dy dx. What is that? Well, what I'm going to do is I'm going to take this 4 and pull it out in front there. Okay, so what I'm going to do when I do that is I'm going to get 4. Okay, I'm going to keep this 3 times x, but since I'm differentiating this, when I have this 4 here, I'm going to take 1 away and it's going to be 4 minus 1, so this is going to be to the 3rd power. So then I can multiply these things out, and 4 times 3 is 12, and this is going to be 12x to the 3rd. Okay? And that would be the derivative of this function. So notice what I did. I took this 4 and pulled it out in front of all of this. That's what this 4 is right there. Then I have 3, and then times x to the 4 minus 1. I'm going to take 1 away from this numerical power right there, and 1 under that is 3. And that's where I got this. Okay? Let's do another example. Here's another function, y is equal to 2x cubed. What I'm going to do now is I'm going to take this 3 right here, and I'm just going to pull it in front right there of the function. All right? So when I take the derivative, I'm going to have this 3 times, and I'm going to keep this 2 right here, times 2, x, but it's not going to be x to the 3rd because I have to take 1 away from this. So it's going to be x to the 3 minus 1, or x to the 2nd. Okay? So when I get everything together, 3 times 2 is 6, and then x to the 2nd, or 6x squared. And this would be the derivative of this function over here. Okay? Now, remember, these were just really, really simple one-term polynomials because there's 3x to the 4th, or 2x to the 3rd in this case, and we didn't multiply them by anything. Actually, if we did that, we may not be able to use power rule, as shown right here, over here. And we're not adding anything, so there's just one term. But what if we actually have a function where I have maybe 4 different polynomials, or in this case 3 polynomials and a constant? What if I have something like this? Okay, so my function is actually 4x cubed plus 3x squared plus 6x plus a constant 5. How do I deal with this? Well, there's a big difference in calculus between adding and multiplying. Okay, the way I would think about it is sort of in your mind, think of adding and subtracting together in your mind. They're sort of kind of the same thing, and you treat them in similar ways. When you're multiplying and dividing, that's something completely different, okay? So if I had a function where I have one term here, I have a second term here, a third term here, and a fourth term here. Now, notice individually this first term, okay, does that satisfy our criteria to use power rule? Yes, has a variable raised to a numerical power. So does this one. This is also a variable x raised to a numerical power. When you see just a simple x, you basically just assume that the exponent there is 1. So this is a variable x raised to a numerical power, and then a constant. And we'll talk about how to deal with the constant last. So in other words, it's sort of like if you have a polynomial term added to another polynomial term added to another one, you actually just take the derivatives individually and then add them. Okay, so what would be the derivative of this first function right here? Well, what I'm going to do is, let me do green, I'm going to take this number 3 and multiply it out in front of here, just pull it out there. So I'm going to get 3 times, and then I'm going to keep this 4 right there, and then I'm going to have times x, but it's not going to be to the third power. I have to take 1 away, so it's going to be 2, right? So then I'm going to add on the next term. What's the derivative of this polynomial function? Well, what I'm going to do now is I'm going to take this 2 right here and pull it out in front and multiply by that. So I'm going to have this 2 there. And then I'm going to keep this 3 here. That's just a constant. I keep that times x. And it's not going to be to the second power. I have to take 1 away, so x to the first, right? And then I'm going to add on the derivative of this next thing. So now I'm going to look at this one. What's the derivative here? Well, now what I'm going to do is I'm going to take this 1, multiply it out there, so 1 times, and then I'm going to keep this 6, all right? And when I take 1 away from 1, that's just going to be to the 0 power. And actually, one important thing is that anytime you see something where it's some variable to the 0 power, that's sort of an identity, and that's just equal to 1. So anytime I have x to the 0 power, so x to the 0 power, this is actually just equal to 1. Okay, anything to the 0 power is 1, all right? And then I'm going to look at this last thing and add on that. And actually, it turns out that whenever I have a number, so it could be 5, it could be 10 million, it could be 157 trillion, okay, I don't know, it could be any number. If I take the derivative of that, it's just 0. Okay, so anytime I have just a simple number, any number, 1, 2, 3, basically out to infinity, if I take the derivative of it, it's 0. Okay? And then I'm just going to basically, all I'm going to do is just take this and just rewrite it a little more neatly. So the derivative is, so I'm going to have this 3 times 4, which is 12, and then it's multiplied by x squared, right? Then I'm going to add on, what's 2 times 3? That's 6 times x, or 6x, all right? I could indicate the 1 there. In some cases, if it helps you, you may keep that. And I'm going to add on the next thing. What's 1 times 6 times 1? That's just 6. And then you could put on the plus 0, but that's not necessary. So as far as we're concerned here, this is the derivative right here. Now what's the key takeaway from this video of using power rule? Well, the key takeaway is, number 1, you have to be able to identify what's applicable for power rule. Okay? And in general, it's things where they're simple polynomials not multiplied by anything that's not a polynomial. Okay? So things like x to the second, x to the 7th, x to the 1000th, 5x to the 9th, 3x to the 10th, anything like that. That's perfectly reasonable. Or if you have the sum of 2 polynomials, so 3x squared plus 4x to the 5th, I think that is, and both of those individually we're able to use power rule on. So maybe one thing to conclude, maybe we should just do a little bit of practice in identifying something that you could use power rule on. So say I had some function f. Let's say the function, and this you could sort of think of this as y, but the function is equal to, let's say, 3x to the 5th. Is this something we're able to use power rule on? Yes, it is, because I have some variable here, x, raised to a numerical power, and there's a constant out in front, but that doesn't matter. So this is something we're able to use power rule on. Suppose I have another function, g is equal to, let's say 4x times sine of x, all right, 4x times sine of x. Well, I do have this thing right here that I think I can use power rule on 4x, but I have something called a trigonometric function over here. And since it's multiplied by that trigonometric function, then the whole thing, this whole term, I cannot use simple power rule on. So no, this one I cannot use this technique that I just showed you on. Okay? Look at another function h. Suppose now, let's say I have, 10x cubed times tangent of x. Well, once again, we have this polynomial 10x cubed, and I think I could use it on that, right? But it's multiplied by another trigonometric function, tangent of x. And since they're multiplied together, no, I cannot use simple power rule on that. Let's say I have another function k, all right? Suppose this one, let's just throw a trick one in here. Suppose this is natural log of x, natural log of x. Can I use power rule on this? Well, no. There's actually no polynomial here to begin with. Okay, it's actually a natural log function. Okay, so if there's a natural log function here and no just simple polynomial, again, you cannot use simple power rule on that. Okay, let me see if I can think of another one. Let's say I have a function m, and let's say the function m is 3x to the 5th times x to the 4th, all right? Now, on this one, okay, you have this x to the 5th, and that's certainly something we can use power rule on, and I have another polynomial x to the 4th. Well, it turns out that, and this is something we're going to do a little bit more practice with in future examples, but whenever you have x to the 5th times x to the 4th, and this is only when they're multiplied, so these are multiplied by each other, x to the 5th times x to the 4th. What I can do is I can actually say this is x to the 5 plus 4, which is actually equal to x to the 9th. And just keep in mind there's a 3 out in front. So whenever you have two polynomials, x to the 5th and x to the 4th multiplied, you can actually combine them into one polynomial, and then power rule is applicable on this, right? Because I have some variable x raised to a numerical power. So this is, you're able to use power rule on that one, all right? Now here's one more thing to kind of lead us into future examples before we conclude this video. And here it is. Suppose now I have a function, let's say it's 7x to the 4th plus, let's say, cosine of x, all right? So 7x to the 4th plus cosine of x. Now, when we looked at what wouldn't qualify as a function, it was something like this. Something like, I'm going to kind of use a similar thing to this. Let's suppose z was a function, and it was 7x to the 4th times cosine of x, right? Times cosine of x. Let me actually do it like this. Times cosine of x, right? And if I asked you, can we use power rule on this, you would hopefully say no. And your justification for that is, yes, I do have this 7x to the 4th, which is polynomial, but it's multiplied by a trigonometric function, cosine of x. So power rule would not be applicable on this. However, for this function that I have written over here, notice that the cosine of x over on the right side is not multiplied by 7x to the 4th, it's actually added. Now think back to what we did over here. When I had a simple polynomial that was added to other things, I just treat each term separately. So if I want to take the derivative of this whole thing, I'm going to take the derivative of 4x cubed, which was 3 times 4 times x squared. and then add on the derivative of the next thing, and then add on the derivative of the next thing. I'm actually going to do a similar thing here. So if I want to find the derivative of this is essentially what I'm going to do. If I want to take, oops, let me actually get rid of the red. I want to take the derivative of n with respect to x. What I'm going to do is I'm going to take the derivative with respect to this, because notice, it's not multiplied by anything that would make this technique invalid, right? So what do? I take this 4 right here, and I multiply it out in front here, so I'm going to have this 4 times, and then I'm going to keep this 7 right there and have x, but the power gets dropped by 1, so instead of 4, it's 3. And then I have to add on the derivative of the next term. Well, the next term you can't use power rule on because it's a trigonometric function. So what I'm going to do then is just I'm going to just say in general I'm going to have to take the derivative of cosine of x with respect to x. We have not talked about how to take this derivative right here. But the key thing is if you have a function that's the sum of two different terms, in other words, this one we would say is term 1, this one, the cosine, is term 2, okay? Actually, let me make that a little neater. So this is term 2 right here, okay? If your function is the sum of two different terms, then you may have to use a different differentiation technique on each term. For example, this first term, I can use power rule on it, and I actually calculated what that is. This is actually 28x cubed, right? This term over here, there's no way to use power rule on. So sometimes when you have terms added in a function, one term you may have to use a different technique on that than a separate term. And in fact, this term is actually something that you normally talk about in the chapter after this. Okay, you don't have to worry about this right now at all. All we're going to concern ourselves with are power rule type of things. In the next video, we're going to deal with how you actually go about finding the derivative of one of these functions that I had shown right here. So these ones are actually a different technique that you use, not in general the simple power rule example. Okay, so hopefully, let's move that a little bit, hopefully this made a little bit of sense and gave you an intuition on what you can use power rule for. Okay, the one key takeaway I want to leave, this goes for anything you do, whether it's derivatives in usually semester 1, or you're doing integrals in semester 2, any technique that you're using, you have to know which functions are applicable to that technique. Okay, so we already basically said if I wanted to do something like if I had a function, let's say my function was, let's say it was, I'm trying to think of one. Let's say the function was e to the 5x. All right, I don't know how to deal with this e. Right, we haven't dealt with that yet, so that would not be something necessarily that I'm going to use power rule on. Right, another function, I could have a function cosine of 3x. Right, cosine of 3x. Again, this is not the type of function that I use power rule on. Right. So is power rule applicable on this first one? No. Power rule is not applicable on the second one either. So a key thing is just to recognize which functions are applicable to use a technique on. So that's actually more important than the technique itself. You have to be able to recognize which functions are applicable for which techniques. And one of the things I hope to focus on in all of the videos that we do is when to do certain things. When do you use this technique? And hopefully you got a feel for when you use power rule. I have to have something like in the form of 3x to the 4th or 2x to the 3rd, and it can't be multiplied by some other weird wacko function like cosine of x or natural log of x or something. Okay, it has to be a simple polynomial, which is some variable x raised to a numerical power, and then it can have a number out in front. Okay, so hopefully this gave you an intuition on power rule. In the next video, we're going to do another technique called product rule, and we will talk about that in the very next video. Hope this helped you get an intuition on power rule. See you in the next video.